this lecture. The topic that will be discussed today is about the plate fin type heat exchangers. This plate fin type heat exchanger is completely a new type of exchanger we have not discussed in the previous lectures, as you will be able to understand from the following slides. So, before going into the details about the plate fin heat exchanger, let us look where it belongs to in the classification of the heat exchangers. So, according to the classification according to the construction, we find that there was a class of exchanger where we had the extended surface heat transfer. There was a class where we had heat exchangers with extended heat transfer surfaces, and one of the derivative of this extended surface heat transfer is of plate fin type, and that is what we call it plate fin type heat exchanger. So, if we look into the other classification where we will be able to find where it exactly it is belonging, you will find that there is a classification based on the surface compactness, and if we look into that classification, we will find that there is a class of exchanger which is compact, and that compactness is defined by a parameter beta, which is defined as a demarcation is between the compactness and non compactness is 700 meter square per meter cube. This classification has been recommended by Professor Arkesha in his classification of heat exchangers in the Heat Exchangers Thermohydraulic Fundamental and Design, that is the book edited by S. Kakak and et al. So, we will be following this nomenclature of calling the heat exchanger as compact if the compactness factor beta is more than 700 meter square per meter cube. So, this particular plate fin type of heat exchanger belongs to that category that it will be more than 400 meter square per 700 meter square per meter cube. Particularly, this is a gas to fluid heat exchanger, and in this region compactness is defined by 700 meter square per meter cube, and we will define it as compact heat exchanger. So, if we now look into the hydraulic diameter from the hydraulic diameter point of view, or if we look into the basic heat transfer equation, we find that the heat transfer is basically related to the overall heat transfer coefficient and the delta T, and this delta T Lm basically the log mean temperature difference. And if we divide both sides by the volume of the heat exchanger, we find that it is giving us Q by V, the heat transfer per unit volume that can be achieved. It is a function of the overall heat transfer coefficient, and not only that, then we have A by V and delta T. Now, this A by V, the area per unit volume, that is what is the beta factor, that is what we are trying to define, and then we also have the log mean temperature difference. Now, this parameter, the amount of heat that we can, the heat load per unit delta T is basically we can find that it is a function of beta and V and also the U. So, if we have a very high beta value, we can expect a small value of delta V, which will be if Q by delta T is constant, is remaining constant, then for a given Q by delta T we have U fixed, and beta if we have a larger value, we can expect that a smaller volume will be able to give us the desired effect. So, that means the heat exchanger can be made compact. So, if we look into that one, so far we were looking into the tubular exchanger, where the typical hydraulic diameter is of the order of this region, where you see this is the plain tubular cell and tube heat exchanger, and on this side the lower fin or etc. strip fin, these are basically the heat exchanger, plate fin type heat exchangers, and the cryogenic heat exchangers or other type of matrix and other heat exchangers basically belong to that compact heat exchanger range. So, hydraulic diameter is of the order of, this is where we have the hydraulic diameter, and this is where we have the surface area density. So, nearly about 700 is the demarcation between the compactness and the non-compact heat exchanger. So, here somewhere here we have the 500, 600, 700, that is the limiting line between the compact and non-compact heat exchanger. So, basically this plate fin type heat exchanger belong to that compact heat exchanger with the typical surface area density more than 700 meter square per meter cube. Now, if we look into the construction of this exchanger, this is a real time heat exchanger. Just to show you how it looks like, we should actually have a length scale. It's a, you can understand that this is the length, and we have one fluid flowing from one end to the other end, directly from this end to this end, and another fluid, it is entering here. It has two exits, it can come out from this end, it can also come out from this end. So, it is also, this is another advantage, or you can say the characteristics of this plate fin type heat exchanger, where multiple exit or intermediate entry and exit can be possible in this type of heat exchanger. Okay. So, in another pictorial view, I will show you here. This is another plate fin type heat exchanger. You can see a glimpse of the fins. These are the fins where we will be discussing about this geometry later on. So, this is the cross flow type plate fin type heat exchanger, where this is made of brazed aluminium. There are two terms, brazed and aluminium plate fin type heat exchanger. This is also a plate fin type heat exchanger, which is made of aluminium, and that aluminium is brazed with each other. So, that it is a special type of plate fin heat exchanger, which is a brazed aluminium plate fin heat exchanger. So, we will talk about this in details. First of all, let us have a look into the details of this, why we go for aluminium, why do we go for brazing of it. So, first of all, this aluminium is one of the good thermal conductivity material with light weightness. This kind of exchangers are widely used in automobiles or in aircraft. So, this weight to strength ratio of this material is always looked after, it is a parameter which we always look for, and we will understand that the brazing is the only option, particularly for the type of fins we are going to join. In case of a plate fin type heat exchanger, we cannot do the regular welding, though aluminum welding it is possible. We cannot do the welding of finned surfaces with the plates manually. So, we have to go for a automatic joining of the plate with the fins, which we will be talking later on. And so, these particular properties like the high strength to weight ratio, this weight is small and its strength is high, and it is having moderately good thermal conductivity. So, we go for, and also it can be brazed. So, that is another favorable parameter. Particularly we go for the aluminum 3003 3000 series, particularly this is the other than any element aluminum, particularly it is a manganese based and its percentage is about 1 to 1.5 percentage of manganese it will be there, and its solidus is 643 degrees centigrade. So, if we have a plate and we will be connecting the fins on top of it, and it is like this, we will be joining, this is the kind of fin we will be joining, and this is the plate material. So, on top of it we want to have a kind of filler material, or the I mean which is this is the brazing material. This brazing material is aluminum plus 7% silicon. So, its melting point, when as soon as we add this 7% silicon, it becomes 590 degree, whereas the solidus of this parent material, this is 643 degrees centigrade. So, that means this filler material will melt fast, but this parent material will not melt at that time, but this difference in temperature is very small. So, we can understand that we need a very precise temperature furnace. I mean furnace, the temperature control in the furnace is very stringent, and we have to maintain the temperature of the furnace. Basically, we will talk about the manufacturing of that brazed aluminum plate fin heat exchanger, we will discuss in details at that time. So, we need to maintain the temperature of the furnace so that this parent material should not melt. I mean it will of course ensure a good, we need to ensure a good brazing between the fin and the plate, but at the same time we also need to ensure that there is no a kind of hole or formation of any leakage, so that one fluid which is flowing on this side and the fluid flowing on this side should not leak, and that is what we need to ensure. So, generally it is vacuum brazed, these units are made in vacuum brazing furnace. So, we need a very stringent temperature requirement for manufacturing this kind of heat exchangers. So, we will come to that part later. So, here is the exploded view for a particular layer of the plate fin type heat exchanger. We have one layer of primary heat transfer surface area. Basically, this is an as I told in the initially that this is an extended type heat transfer surface. So, according to that classification, we have a primary heat transfer surface area, and then this is what is the primary heat transfer surface area. Now, we have another primary heat transfer surface area on this side, and between this primary heat transfer surface area we have the extended heat transfer surface area or the fin. So, in between these two plates or the primary heat transfer surface area we have some fins or extended heat transfer surface. So, now the purpose of this fin is, and here what we have is something called sidebar. This is what is sidebar, on this side also it is a sidebar. So, that means it is basically like this, that we want to make a channel. This channel is made of one primary surface area, another primary surface area. In between what we have is the fin. This fin is serving both the purposes of, or it has double, I mean the purpose of this fin is basically to provide extra or extended heat transfer surface area. At the same time it gives a mechanical stability or construction stability, like it gives some strength to the construction, so that under pressure this will not bulge. So, this mechanical stability of this one will also be purpose for this one. So, now you can understand that each of this surface is to be adhered to this plate, and this one has to be adhered to this plate. To have a good thermal joint, we need a good thermal contact between these two, otherwise there would be, when the heat is getting transferred, so there would be a resistance between this fin and the plate. So, that is not desirable. We want this fin to be completely attached thermally to this upper surface. So, we need a good bonding between this point, this point, this point, and in fact, all the surfaces should be adhered to this primary heat transfer surface area, and these fins are to be attached. So, it is understandable that it is not possible for someone to make a physical joint, because it, first of all, it will not be accessible. Even if it is not accessible, even if it is accessible, it is impossible to make or ensure that each and every point of it is joined with the primary surface area. Now, as you can understand that we have two primary surface area, in between we have the fin, and now imagine this is the cross sectional area, and we have say a fluid flowing from this end to the other end. So, we have to ensure that the fluid is not spilling over from this side or this side, it should not go out of this one. So, what we need to do for this purpose, that we should have a kind of sidebar on both the ends. So, this will be, we will put a barricade on this side and another barricade on this side. So, we are confining the liquid within this zone, and this zone is created by this one, where we have the primary surface area and the fin, and it is bounded by two sidebars. So, this is the exploded view for a particular layer, and so we can expect that on top of it we will put another layer. So, that will form the, this is an exploded view of the two layer one. So, here what we have is one fluid, this is the primary surface area, this is another primary surface area, these are the primary surface areas, and we have one fluid flowing from this end to this end. So, these are the extended heat transfer surface area fin, and now imagine we have put on top of it another layer, where this is the plate which is the primary area separating this fluid to mix with this fluid is entering from this end, and we have another separating plate on this side. So, for this fluid, this is the sidebar, for this fluid we have this sidebar, and on this side we have another sidebar. So, between this two primary surfaces we have fin and two plates, two sidebars. So, this is one channel for this fluid. Similarly, on the other side what we have is this primary surface area, and then we have, this is the primary surface area, and what we have here is, I am sorry, this is one surface area, then we have another surface area here, this is the confinement, this is the sidebar, these are the two sidebar, and these are the fins. So, this whole unit becomes an exploded view, and this is for this particular channel is meant for this fluid. So, like this we have this fluid getting distributed between several layers, and this is for, if it is, this layer is designated for this channel, and the alternative will again be for this fluid, say if we call it fluid number 1, and this is say fluid 2, we have this channel designated for fluid 2, the next channel will be designated for the fluid 1. So, like that we have this is a 2 fluid stream heat exchanger, and as you can understand that each fluid flow is taking place at 90 degree. So, it is a cross flow arrangement. So, when we talk about the flow arrangement, we will come in details. So, this is the exploded view, and like this we make a stack of the heat exchanger, and then we go for the complete heat exchanger matrix or something like that. So, here what we have is the plate, this is the plate, this is sidebar, these are the fin, and as the name suggests, the plate fin comes from this nomenclature. I mean this nomenclature, this is fin, this is plate, and as a whole this unit becomes a plate fin heat exchanger. So, this is a typical brazed aluminum plate fin heat exchanger. We can have a look into this small video. This is a brazed aluminum plate fin heat exchanger. So, here as you can understand that this is the sidebar, we are not able to see this particular area. So, the fins are located at this point, these are the fins. So, this channel through which the fluid is flowing, you will find that this is blocked at this end and this is blocked at this end. So, that the fluid is flowing in this direction. So, this is basically nothing but the rectangular hollow header, which is allowing the fluid to come on this side and allow the fluid to flow through this end and this black colored one, whereas that white one is basically nothing but the sidebars. So, if we look into the video, this is the other side, we will come to, we will look into these details. So, now you see this is what is the sidebar, and the corresponding side on the other end, I mean just we have come from that end to this end, you find that this is the plate or the primary area, and with that primary area, between these two primary area we have the fins, they are adhered to each other, I mean with the it is brazed at this point, and this is particularly this is an wavy fin, and here we have a sidebar. So, this is a sidebar. If you look at this end for this particular fin, this geometry, this end you have, it is not visible at this position, this end and this end it is blocked. So, these are the sidebars. So, when the fluid is flowing in this direction, the fluid will flow these channels through these channels, through this channel it will flow through, and it will not pass or mix with the sidebar, or this is the sidebar, this is another sidebar, these are the sidebars, and the fluid is not able to mix with the fluid flowing on the other side through this channel. So, basically this is again a cross flow type heat exchanger, where we have both the fluids, I mean not mixed, it is unmixed, both the fluids unmixed, and this is basically you can understand that this is of slightly longer length than this particular one. So, this is wider, this is smaller. Okay. So, now what are the advantage of this particular type of heat exchangers? The advantage of brazed aluminum plate fin heat exchanger, as we have discussed earlier, that it is a compact heat exchanger. So, it has a very high heat transfer surface area density, and it is most of the time it is more than 700 meter square per meter cube. That means, we get very good compactness. In fact, you will find some of the cryogenic heat exchangers, they are quite really big, but if they were not compact, they would have been still bigger in size. So, as compared to this surface area density, we have relatively low pressure drop. Any heat exchanger designer, they will try to make a heat exchanger where we have high heat transfer, but the pressure drop penalty is comparatively smaller. So, here we have the thermal performance, desirable thermal performance of the heat exchanger, but not a very high at the cost of large pressure drop. So, it is having a moderate pressure drop, and since it is made of aluminum, we have the low weight for this heat exchanger, and it is not really very costly, though the particularly the fabrication technique determines its cost, and the number of units which are made on the size of the heat exchanger, that determines its cost. And we have another big advantage of this particular type of heat exchanger is that it can handle large number of stream in a single unit. So, basically that makes this plate fin type heat exchanger a multi stream heat exchanger. So, it handles multiple streams, multi-stream heat exchanger. So, multiple stream heat exchanger accommodating multiple streams within a single unit is obviously advantageous. So, we will later on see how this plate fin heat exchangers allow the handling of multiple strings within a same unit. Then we also have the advantage, particularly with respect to this plate fin type heat exchanger, is that we have the intermediate entry and exit of the fluid streams. So, that gives a big advantage or flexibility in the handling of the fluid streams. So, not only it handles multiple streams, it also helps intermediate entry and exit of the fluid streams in the heat exchanger. So, next is its application. Where are the places where we find its application? So, in most of the cryogenic process plants these days, cryogenic liquefaction plants, then air separation plants, then we have the regenerators, and as I told you, this is the air separation plant. We have the main heat exchangers where the air is being handled, and then we have the condenser reboiler in between the double column unit. So, the condenser reboiler earlier used to be a shell and tube type or tubular exchanger. These days you will find frequently that these are replaced by plate fin type heat exchangers. So, most of the cryogenic process plants heat exchangers are of very high effectiveness, and most of the time we look for heat exchanger effectiveness around 0.9 to 0.95 or so. Otherwise some of the processes will not at all start if the heat exchanger effectiveness is very small. So, we have very stringent requirement for the heat exchanger effectiveness in case of cryogenic heat exchangers. So, we find that brazed aluminum plate fin heat exchangers meet that requirement of high effectiveness heat exchangers in cryogenic engineering. Moreover, in aircrafts the requirements are slightly different. Here you will find that the heat exchanger effectiveness is not that high, but it need to be very lightweight. and there the air conditioning, hydraulic and lube oil coolers, in the ram air cooling etc. are done in case of heat exchangers made out of brazed aluminum, and sometime it is brazed stainless steel to meet the high temperature requirement of the handling high temperature requirement in the aircrafts. We find that some of the exchangers are made of stainless steel. Then in automobile radiators, we find that frequently these days we are using the brazed aluminum plate fin type of heat exchangers, and in chemical process plants where we have gas to gas service. This is particularly important. Why do we go for a gas to gas heat exchanger? Why should we restrict it to the gas to gas? As you can understand that the hydraulic diameter or the fin passage is being very small. So, we have a requirement of basically clean fluid. So, if any kind of darts or contamination is there in the process stream, you will find that those flow passages are getting choked, and if anything such happens, often it is not possible to clean it if it is not getting dissolved through some of the chemicals. We will find it is not possible to get it cleaned. So, this cleanliness of the process fluid streams is one of the primary requirement for this kind of heat exchangers, and in chemical process plant where the gas and gas to gas particularly service where it is mostly clean, and you will find that brazed aluminum plate fin type heat exchangers are frequently in use. Another while talking about the limitations or applications of this brazed aluminum plate fin type of heat exchangers, we can understand that when it is brazed aluminum plate fin heat exchanger, obviously its high temperature requirement is limited. It cannot go more than something like its solidus temperature, similarly or very close to the same solidus temperature. But on the other hand, in that case you need to go for the stainless steel type brazed stainless steel plate fin type heat exchanger. And moreover, as you can understand from the construction of this kind of plate fin type heat exchanger, that probably you cannot go for very high pressure. When the process streams are of very high pressure, we cannot really recommend the use of this plate fin type heat exchangers. So, it is the moderate to low pressure when it is the exchangers are of very good use. So, now what are the fin types? There are why should there be any fin, and particularly when we talk about the fin or the extended heat transfer surface, these fins, as I told you, it gives a mechanical stability and also it gives extended heat transfer surface. So, if we look at that again that equation, if we look at Q equals to U into A into delta T, often this delta T Lm is dictated by the process stream. We cannot really have a control on this log mean temperature difference. We may not have much control on the overall heat transfer coefficient. So, we have to manage with this area, heat transfer surface area. So, we augment the heat transfer surface area with the extended surface heat transfer. So, this is what is this fin. The role of this fin is to enhance the heat transfer surface area along with the mechanical stability or the construction stability. So, not only that, it has a third purpose. When we have a straight rectangular plain rectangular fin, we find that the flow will be developed within a few millimeter, or depending on its size the entrance length after the entrance length the flow is fully developed and there is a constant heat transfer coefficient for the entire region. Now, what we need to do is that if we want to change the heat transfer coefficient, if it is a regular or rectangular plane fin channel. So, we do not have that option of breaking that boundary layer. So, that is also true in case of plane trapezoidal fin. So, after certain entrance length we find that the flow is fully developed and there will not be any change in the there is no change in the fin geometry. There is no change in the heat transfer coefficient because of it is fully developed. But in case of strip fin geometry, we find that the flow is it is slightly offset, as we can call it offset strip fin. This is slightly after certain length, this is called the lance length. After this lance length, this is known as lance length. After the lance length, this as you can understand that as if the flow passage has been shifted, it has it was flowing like this. Now, suddenly the path has been broken and it has been shifted like this, this channel is been shifted. So, after coming the flow after coming over here, it finds that there is another fresh generation of the fresh boundary layer at this point. Similarly, again after going at this point, it will find that there is the flow has to be developed at this point. So, like that the flow is getting developed at every regular interval, and in this offset strip fin this purpose of this offset strip fin is to not only enhance the heat transfer surface area, not only give the mechanical stability, it also enhances the heat transfer surface area just because of the fin construction. So, another fin is of use, that is wavy fin. In this type of fin, it is a continuous fin. Here you can see there is a discontinuity in the fin, we are interrupting the fin at regular interval, but in this type this is the continuous fin geometry, but still its waviness gives us the desired flow separation at regular interval and breaking of the boundary layer at regular interval, causing enhancement in the heat transfer surface and heat transfer coefficient, and along with the enhancement in the heat transfer surface area, we get enhancement in the heat transfer coefficient. So, this is a wavy fin. Along with that, we have perforated plain perforated heat exchanger. So, in the rectangular, it is not shown here, in the rectangular plain rectangular fin, if we have perforation on this surface at regular interval, if we make perforations. So, then we find that it is also a kind of interrupted fin. So, the fluid will come here and it will have a passage, or it is or this flow will try to go inside, or that fluid will try to come out of that perforation. So, thereby giving a breakage in the boundary layer. That also we often use in plate fin type heat exchangers. Thank you for your attention.